Now assume we are having the following keys, following data: 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now if the keys, this every data, every single element, I am calling it as a key. So in most of the cases they are also called as key. So if all these keys are given in this order, that means in the increasing order, then try to create a binary search tree from this. So if you try to create, then the binary search tree will look something like this: 1, so 2 is greater than 1, so it will come to the right. So 3 is greater than 2, so it will come to the right. Again 4 is greater than 3, then 5, then 6, then 7, then 8 and then 9. So this is how a binary search tree look like when all the data is given in increasing order. So assume if the data is given in decreasing order, assume the data given is 9, 8, 7, 6, 5, 4, 3, 2, 1. Then how will the binary search tree will look like? So this is 9, 8 is less than 9, then 7 is less than 8, then 6 is less than 7, then 5 is less than 6, then 4 is less than 5, then 3 is less than 4, then 1 is less than 3. Okay, so if you look at them closely, then these trees will look something like a linked list, right? So in case of linked list, if you try to search any data, then you have to do a sequential search, right? In that case, searching will take order of n time, right? In this case also, if you have to do some sequential search of the data, then it will take order of n time, right? But why do we use binary search trees? Because we wanted to minimize the search time complexity, right? So in the case of binary search trees, we want the search time complexity to be order of log n, but here the search time complexity is only order of n, right? So in this case, you can see these binary trees are not balanced, right? So because these binary trees are not balanced, the time complexity is actually increased as compared to this log n. So time complexity is order of n as compared to order of log n. So how can we make these binary trees as balanced? Okay, so to make these binary trees as balanced, we introduce a new concept, and that concept is for AVL tree. And this AVL tree is actually given by this scientist, which is Edelson, Valesky and Landis. So these AVL trees are actually named after this scientist. Okay, so now let us see what is an AVL tree. In an AVL tree, there are two conditions. Number one condition is these AVL trees are actually, it is a binary tree. It is a binary search tree actually. Binary search tree. And second condition is the height of the left subtree, okay, and the height of the right subtree differed by minus the height of the right subtree should be actually between -1 to 1 only. Now if their height is greater than this, then the tree is not balanced. They define the balance factor like this. So this is actually called as a balance factor. Okay, so what is a balance factor? Balance factor is height of left subtree minus height of right subtree. In sub books, you can also find out the balance factor is actually height of right subtree minus height of left subtree. Okay, and both of them are actually correct, right? Because in any case, it should be between -1 to 1, right? Now let us see how do we find out this balance factor. So if I just write for this equation actually before that, so it is balance factor should be between -1 to 1. So when the balance factor is exceeding these limits, then the tree is not balanced. Now assume that we are having this binary tree. So binary tree is B, A and C. Now for this binary tree, in case of AVL tree, what we are going to do is whenever we have to find the balance factor, we'll assume that the height of the leaf node is 1 instead of 0. Okay, so this is just an exception because in that case it will be very easy to find the balance factor. Okay, you can do it with 0 also, but in that case it will be easy. So Here the balance factor is 0 because there is no left subtree and there is no right subtree. So I am finding the balance factor for every node. Okay. For this node the balance factor is 0 because there is no left subtree and there is no right subtree. So it will be 0 minus 0 is 0. Okay. Now for this node B, the balance factor is actually 0. Why? Because the height of the left subtree minus the height of the right subtree. The height of the left subtree, I am assuming that the leaf nodes are having the height as 1. So it will be 1 minus 1, which is going to give us 0. Okay, now assume that we are having this tree which is C, B and A. Now for this tree, for this node A, what is the balance factor? So balance factor for this node A is 0 because there is no left subtree and there is no right subtree. So height of the left subtree minus height of the right subtree is going to give us 0. For this B, what is the balance factor? For this B, there is only a left subtree but there is no right subtree, right? So it will be 1 minus 0. Okay, so the balance factor is 1 here. Now for this C, the balance factor is actually height of the left subtree is going to give you 2 and the height of the right subtree is 0. So the balance factor is actually 2 minus 0 is equal to 2. Okay, so if you see here in this node C, the balance factor is actually exceeding the limits of this minus 1 and plus 1. So balance factor should always be between minus 1 and plus 1, and this 2 is not actually minus 1 and plus 1. So here we can see that this tree is not balanced, right? Now let us take an example of one more tree. So assume that we are having this tree. It is some data 9, 6, 8, 7, 5, 4. It is having 2, 1 or 7. Okay, now let us try to find the balance factor for this tree. So we are not actually, for this tree we are not trying to balance this tree, we are just trying to find out what is the balance factor here. Okay, so later on we will be seeing how to balance a given binary tree. Okay, so in this tree, for this node B and for this node 4, it is a leaf node, therefore the balance factor is 0. Here this 8 is a leaf node, therefore the balance factor is 0. This 1 is a leaf node, therefore the balance factor is 0, and this 7 is a leaf node, therefore the balance factor is 0. Now for this node 5, there is no right subtree, there is only left subtree, therefore the balance factor is 1 because height of the left subtree minus height of the right subtree. For this node 7, there is no right subtree but there are left subtrees, right? Left subtree. So for this 7, the balance factor is actually 2. For this 6, what is the balance factor? The balance factor is actually 2, right? Because it is 3 minus 1 is 2. For this 2, what is the balance factor? The balance factor is actually 0. And for this 9, what is the balance factor? Balance factor is given by the height of the left subtree minus height of the right subtree, right? Therefore here the balance factor is actually 2. So because there are multiple nodes with the balance factor as 2, therefore this tree is not balanced. Okay. Now if you see logically, then you will find out that for a given tree, for a given node, let us suppose this is a node X, then to find the balance factor for this node, there is a left subtree and there will be some height of the left subtree. So let us assume that height is given by this weight, like this. This is a weight, okay, and there is a right subtree which is having some height. Okay, now you can assume it like a a tarazu in Hindi. So if one side becomes heavy, that tarazu actually shifted to one single side. So we do not want this to happen like this. So we want it to be stabilized in both the cases. That means that the balance should be maintained in both these cases, right? So what happens is, whenever we try to insert a node in a given binary tree, there are some anomalies which occur, and we try to remove those anomalies, right? So what will happen is there are few anomalies which there are actually 4 types of anomalies. So the first anomaly is left right right. The second anomaly is left left. The third anomaly is type of right left, and the fourth anomaly is type of left right. Okay, now let us see all these anomalies one by one. So the first anomaly is right right. So in this case, when a tree looks something like this, there is a node here, and then there is a node here and then there is a node here. Okay, that means for any given node, for example, this is the node which is containing A, this node is containing B, and this node is containing C. For any given node, all the nodes which are present in the right side, here all the nodes are present in the right side, and here if you try to find out the balance factor, the balance factor for C is actually 0, the balance factor for B is actually 1, and the balance factor for A is actually 2. Right, so because the balance factor of A is actually 2, therefore you can say that this tree is not balanced, and this is called as a right anomaly, because a tree is actually, as you can see, both the nodes are in the right side. Right, so what we will do this in this case is we are going to rotate this tree to make it balanced. So how will you rotate it? You will make this rotation like this. Okay, so the tree will become something like this: B, A, and C. Okay, now if you try to find the balance factor in this case, so the balance factor for this C is 0, the balance factor for A is 0, and the balance factor for B is also 0. So this is called as a right anomaly, and this anomaly can occur anywhere. Okay, and next is the left anomaly. So what is this left anomaly? So when a tree looks something like this, there's a node here. Assume that the node is C, there's a node here which is B, and there's a node here which is A. Now in this case, the tree is tilted toward this left side, so this is left and left, right? So that is why it is called as a left anomaly. So in this case of left anomaly, what we are going to do is we are going to rotate it like this, right? So this rotation will be there. Okay, so after this rotation, the tree will look something like this: B, C, and A. Now if you try to find the balance factor, then the balance factor for this node is 0, the balance factor for this node is 0, and the balance factor for this node is also 0. Okay, now let us see what is this right-left anomaly. Okay, now assume that you are having a tree something like this. Some node here, it is 4, it is containing 2, then we are having a node which is containing 7, then we are having a node which is containing 6, a node which is containing 8, and a node which is containing 5. Now let us try to find the balance factor for these nodes. For this 5, the balance factor is 0. For this 8, the balance factor is 0. For this 6, the balance factor is actually 1. For this 7, the balance factor is also 1. For this 2, the balance factor is 0. For this 4, now for this node 4, the balance factor is 2. Okay, now if you see, this tree is not balanced, right? So this tree is not balanced, and we have to balance this tree. Okay, so what we will do is, here in this case you can see the anomaly. So it is right and this is left anomaly. So this is right and left anomaly. Okay, now in this anomaly, initially what we are going to do is we are going to do a right rotation. Okay, so what will happen in right rotation? This 6 will come to this place, and then we are going to move the 7. Okay, so this tree will now look something like this: 4, 2, 6, and then this 7 is greater than 6, therefore 7 will come here. This 5 is less than 6, therefore 5 will come here, and this 8 is greater than 7, therefore 8 will come here. Okay, don't worry if you don't understand how I did this rotation, because I'm going to write a program for this, and then you can easily understand how I've done this rotation. Okay, now after this, this anomaly is actually changed. Now if you try to find the balance factor, then balance factor is 0. Here the balance factor is -1. Here the balance factor is 0, and here the balance factor is again -1, and here the balance factor is actually -2. Okay, now here if you see, then this anomaly is actually left rotation like this. Okay, so we are going to make a rotation like this. So in this case, what will happen is 6 will come in the root, then in the left part we are having 7, in the right part we are having 7 and 8. In the left part the 4 will come, so 4 will come here, and the left part of 4 will there is a 2, and now where this 5 should come. So this 5 is actually less than 6 and it is greater than 4, therefore 5 should come here. Okay, now this tree will look something like this. Okay, and this next anomaly is left right anomaly. So let us see what is a left right anomaly. So in case of left right anomaly, our tree will look something like this. Assume it is 8, it is 2, and then we are having 5, here we are having 6, here we are having 7, and here we are having 3. Now in this case, if you see the balance factors, the balance factor for this node is 0, the balance factor for this node is 0, the balance factor for this node is 0, and the balance factor for this node is actually -1. The balance factor for this node is -1 again, and the balance factor for this node is 2. Okay, now in this case you can see this tree is not balanced. So what we are going to do is we are going to do a left rotation in this case. So this 6 will come here, and then we have to adjust the position of the other nodes. Okay, so how this tree will look after this? So this A will be here, 2 will be here. So instead of 5 we have to put 6 in that position. So 6 will come here, then 5 is less than 6, so 5 will come here, and 3 is less than 5, so 3 will come here, and then there is a 7 here. Okay, so this is a tree now, new tree, after doing this left rotation, right? Okay, and then let us try to find the balance factors. For this node the balance factor is 0, for this node the balance factor is again 0, for this node the balance factor is again 0, for this node the balance factor is actually 1, for this node the balance factor is 1, and for this node the balance factor is 2. Now to balance this case we have to do this rotation, that is a right rotation. Okay, so tree will look something like this after this one. So 6 will be in the root, and there will be 8 here, 2 here, now 5 was here, and 3 was here. So now 7 is greater than 6 and less than 8, therefore 7 will come here. Now if you try to find out the balance factors for this complete tree, then you will find out that this complete tree is actually balanced. Okay, now in some books they will be using different terminologies for this left rotation, the right rotations, right? Then don't be confused from this left and the right rotations. Okay, so let me just show you how everything works together, and then we'll see some of the programs for this. Okay, assume that we are having some data which we need to insert in this AVL tree. So the data is 1, 2, 3, 4, 5, 6, 7, 8 and 9. So assume that we have to insert this data into this AVL tree. Okay, so initially we are getting 1, so there will be a node which is creating 1. So in every case, whenever we are going to insert a node, we have to check the balance factor. So if the tree is not balanced, then we have to balance this tree again. So here 1 is there, so balance factor for this node is actually currently 0 because it is a single node. Now let us add 2 to this node. So it will look something like this, 1 and 2. So for this node the balance factor is 0. For this node the balance factor is actually -1. Okay, now the next node data is 3, so it is 1, 2, 3. Now for this node the balance factor is 0. For this node the balance factor is 1. For this node the balance factor is 2. Okay, and now you can see that this tree is not balanced, correct? So if this tree is not balanced, then you have to find out what is the anomaly. So this anomaly is actually the right anomaly. So in this case what you have to do is we have to do a left rotation like this. Okay, so the tree will look something like this: 2, 1, and 3. Now try to find out the balance factor. So it is balance factor is 0. Here also the balance factor is 0. And here also the balance factor is 0. Now let us see what is the next data. The next data is 4. So 4 is greater than 2. It is greater than 3. Therefore 4 should come here. Okay. The next data is 5. So before adding that 5, let us see what are the new balance factors in these cases. So when 4 is added, so here the balance factor is actually 0. For this 3, the balance factor is actually -1. For this 2, the balance factor is -1. So still the tree is balanced. Okay. Now let us try to add 5 in this tree. So tree was this, and we are trying to add 5. So 5 is greater than 2. It is greater than 3, it is greater than 4, therefore 5 should come here. Now let us try to find the balance factors. So here the balance factor is 0. Here the balance factor is -1. Here the balance factor is -2. And let me just write it clearly. So it is -2. And here the balance factor is 0. And here again the balance factor is -2. Right? In this case, you can see that the tree is unbalanced after this location, from this location, right? Therefore we have to balance this tree. Now if you see this, see it closely, then you will find out that it is something like right unbalancing, right? So if you are having this right unbalancing, what we are going to do is we are going to rotate this node like this. So the tree will look something like this: 2, 1, 4, 3, and 5. Correct? Now let us try to add the next data. Before that, let us just find out the balance factors here. So balance factor here is 0. The balance factor here is 0. So here the balance factor is 0. Here the balance factor is 0. And here the balance factor is -1. Okay. Now the next data is 6. So if we add 6 to this, then 6 will come somewhere here. So when 6 will come here, in that case, let us try to see if this tree is balanced or not. Now for this 6, what is the balance factor? Balance factor is 0. For this 3, the balance factor is 0. And for this 1 also the balance factor is 0. For this 5, the balance factor is -1. For this 4, the balance factor is -1. For this 2, the balance factor is actually -2. Now what we have to do in this case? In this case, we have to rotate this thing, right? If you see it closely, then you can find out that this is a right anomaly. Okay, this is a right anomaly. This is not a right left anomaly. So when it is a right anomaly, what you have to do is we have to rotate this node like this. So if you rotate this node, then it will look something like this: 4, 2, 1, 5, 6, and then this 3 will come to 3 is actually less than 4 and greater than 2, therefore 3 will come here. Okay, now let us try to find the balance factors here. So here the balance factor is 0, balance factor is 0, balance factor is 0. For this 5, the balance factor is -1. For this 2, the balance factor is 0. For this 4, the balance factor is 0. Now the next data is 7. Let us try to add 7 here. So if we try to add 7, then 7 should come here. So if the 7 will come here, then the tree will not be balanced anymore. Why? Because for this 7, the new balance factor will be 0. For this 6, the new balance factor will be -1. For this 5, the new balance factor will be -2. And for this 4, the new balance factor will be -1. Okay, so what we will do is we'll go from the leaf to root, and as soon as we find that the tree is unbalanced, in that case we are going to identify that this is unbalancing and we are going to balance the tree. Okay, so here this is a right anomaly. So what we are going to do is we are going to rotate this like this. So what will happen? The tree will look something like this: 4, 2, 1, 3, 6, 5, and 7. Okay, now if you see the complete tree is balanced. Now the next data is 8. So 8, if we add 8 to this tree, then 8 will come here. After that, let us see the balance factors. So here the balance factor is 0, balance factor is 0, balance factor is 0, balance factor is 0. For the 7, the balance factor is -1. For 6, balance factor is -1. For this 2, the balance factor is 0, and for this 4, the balance factor is -1. So the tree is completely balanced. Now let us try to add 9. So when we add 9 to this, so 9 will come here. So in that case, let us see if the tree becomes unbalanced. So here the balance factor is 0, here the balance factor is -1, and here the balance factor is -2, and so on. So balance factor, they all will not be balanced because here we are getting unbalancing. So if you see this is a right unbalancing, then we are going to do this rotation, right? Therefore the tree will look something like this: 4, 2, 1, 3, 6, 5, 8, 7, and 9. Now you can see, if you try to find the balance factors for this tree, then the tree is completely balanced. Okay. Now let us try to see an animation for this, and let us try to see if we get the same tree as we are getting here. Okay. Okay, so this is an AVL tree. So let us try to add one here. So one is added. If we add 2, if we add 3, so try to match this with our figures. Okay. If we add 4, if we add 5, now if we add 6, okay. Now if you add 7, add 8, now add 9, okay. So after this we got the complete tree same as we drawn in the diagram. Okay. Now let us try to take more examples to see this AVL tree.